Hello guys, I am here to present a simulation of asynchronous counter, especially for Modulo 10 and 12 ripple counter along with my teammates mentioned here. Firstly, what is counter? A counter is a sequential circuit which can count any particular event on the basis of how many times the particular event is occurred. It is the application of flip-flop. Why? Because counter of made up of flip-flop only. Based on the clock applied for their function, it is classified into asynchronous and synchronous counter. Before jumping into the ripple counter, let's get familiarized with the terms synchronous and asynchronous or ripple counter. In ripple counter, flip-flops are connected in such a way that output of the first flip-flop drives the clock of the next flip-flop. But here, there is no connection between output of the first flip-flop and clock of the next flip-flop. Flip-flops are not clocked simultaneously, but in synchronous counter or clocked simultaneously. Circuit is simple for more number of states. Here, circuit becomes complicated as number of states increases. Speed is slow as clock is propagated through number of stages. Here, speed is high as clock is given at the same time. Now let's see about ripple counter. Ripple counter is the asynchronous counter. It got its name why? Because clock pulses ripple through the circuit. Here different flip-flops are used with the different clock pulses. All the flip-flops are used in toggle mode. Toggle mode is nothing but it changes the output from 0 to 1 or 1 to 0, which means when it is in 0 state, there is no toggle, but when it is in 1 state, it is toggled, and again when it is 0 means it comes under the state like this. In this ripple counter, only one flip-flop is applied to the external, which are as clock pulse LSB in the counting sequence. Now move on to modulo n ripple counter. The modulo n ripple counter forms by combining n number of flip-flops. It is nothing but if I take a 3-bit counter, it requires 3 flip-flops. If I take a 4-bit means it requires a 4 flip-flop to construct it. The mod n ripple counter can count 2 power n state. It is a 2 power n and then it is resets to its initial value. An n-bit counter that count up to its maximum modulus 2 power n, it is a 2 power n, is called full sequence counter. Which means if I take n equal to 2, there are the number of possible states are 2 power 2, which means 4. There is a 4 number of possible states which is equal to full sequence counter. This is called as mod 4 counter. An n-bit counter whose modulus is less than maximum possible is called truncated counter. If I take a, if I take a 4 bits, I get a 16 possible state, but I want a modulo 10, modulo 12, modulo 13 like this, but there is a number of states are decreased here, which means it is called. Later we will discuss the example of truncated counter. Now coming to the ripple counter, I take a 4-bit ripple counter which counts up to 0 to 16 state, which means 16 possible number of states are present here. On the 15th count, it comes back to 0 as already saw. See, the n model counter, ripple counter can count 2 power n state and then the counter resets to its initial value. The initial value is 0. On the 15th count, it counts back to 0. Now, let's see the modulo 10 and modulo 12 ripple counter. Modulo 10 means it is the truncated counter which counts up to 0 to 9 states. On the 10th count, it's come back to 0. For the modulo 10 counter, it counts up to 0 to 11th state. On the 12th count, it's come back to 0. Moving on to the simulation part, I have already given the circuit connection as per the circuit diagram. I have used the software called Multisim 14.2 version. Firstly, we can see the up-down up counter. The components whichever I used here are this. Firstly, I want a 4JK flip-flop. For that 74LS76D is used. From TTL I can get the flip-flop. You can see the number of IC and just type it and get it. Secondly, clock voltage. Clock voltage, which is the only external source applied to the first flip-flop. From where I can get means go to the source and signal voltage sources and clock voltage. Next, I want a ground. Go to the same source and power source. Go to the ground, get it. Next, digital display means go to the indicators. From where indicators and DCD digital green. I have used green color. You can get any color. Since it was the 4-bit, I have used the hexadecimal digital display. Nextly, I want a probe, which is also from indicator. Just type a probe and get the color whatever you required. Sorry. Next, I have want interactive digital constant, which is the digital input 0 or 1. From where I can get means go to the source and digital sources and interactive digital constant. Just put it and give OK. Now let's see the connections of the circuit. Firstly, as we studied about asynchronous counter, the output of the JK flip-flop is given as the input of the clock in the next flip-flop. Like the manner we have given the circuit connection, and preset and clear is the main thing in the JK flip-flop. For the JK flip-flop, preset input is used to directly put a 1 in the Q output. Next, clear input is used to directly put a 0 in the Q output on the JK flip-flop. For the indicators, we have used the lights, and the only external clock is used here as we studied. Now simulate this. It is the 4-bit counter, so it counts up to 0 to 15. It is the LSB side, it is the MSB side. Usually LSB is connected in the external clock where external clock pulse is connected. Like this, till 9 it displayed in number. After 9 it display in A, B, C, D for the 10, 11, 12, 13, 14, etc. It's all about the ripple counter and verified with the truth table. Now moving on to the mod 10 ripple counter. Here I have used one AND gate for the counting. It counts up to 0 to 9 and 10 states are possible. At the 10th count it coming back to 0. We will see in simulation. See, the simulation is, it counts up to 0 to 9. Let's see. Sorry, it is the, see, 0, 1. For fast counting, I can change the frequency and I can get the fast counting. I change the 300 millihertz to 600 millihertz. Now see. Okay, I restart the counting. See it how fast how it count. 0, 1, 2, 3, 4. 5 up to 9 it counts, since it was a 10 modulo 10, 8, 9, and after 9 it comes back to 0. See the difference. And one thing is, in an AND gate, the output of the one AND input of the one AND gate is connected to last flip flop, and I mean it is the fourth bit, and second output is connected to the second bit. Likewise, connection in this modulo 10. Now let's see the modulo 12. For the modulo 12, the only difference is the AND input is one is in fourth bit and another one is also in fourth bit input. There you can see it was one in output of the last flip flop, and another one is output of the second flip flop. But in 12 modulo 12, it is in opposite manner. Both input and output of the same flip flop is used. Now let's count. It is the modulo 10, so it counts up to 11. For the 12th count, it comes to again 0. See, 9, 10. After 9, it comes to A, B, C. A, B only it counts, because 10, 11 only it counts. Then 12th count, it comes back to 0. That's all about the simulation. At last we come to the end. I hope you have understood the simulations of ripple counters, especially modulo 10 and 12. Thanks for watching.